All right, good evening, everyone. Thank you so much for joining us today. My name is Harriet Bredel. I'm the Exec Director of the Keck Institute for Space Studies. Really appreciate you joining us for this fantastic guest lecture. Our speaker has come all the way from Japan to join us today to talk about sample return missions from small bodies. Before we do that, I just want to tell you a little bit more about the Keck Institute for Space Studies. We are a think and do tank that's based here on Caltech campus, and we work together to bring scientists and engineers from Caltech, JPL, and the wider community to develop innovative new space missions and technologies for the future. As part of that, we have a series of guest lectures, of which our speaker is here today, but we also support a number of study programs that cover a wide range of space-related topics, and we've got a number of guests here today who are joining us for the full week to talk about sample return missions from all across the solar system. So we've got a number of fantastic experts in the room as well, which is super. To introduce our speaker, I would love and be honored to introduce Yuri Tamara, who is one of our KISS affiliates here at the Institute. She is also a graduate student in planetary science. Geophysics, thank you. A graduate student in geophysics. And with that, I will hand over to Yuri. Thank you very much.
Thank you, Harriet. My name is Yuri, and I have the pleasure and honor of introducing today's speaker, Dr. Shogo Tachibana. Dr. Tachibana is a professor of cosmochemistry at the Organization for Planetary and Space Science and the Department of Earth and Planetary Science at the University of Tokyo. He is also a specially appointed professor at the Institute of Space and Astronautical Science in JAXA. His research focuses on the origin and early evolution of the solar system. Specifically, he investigates the kinetics of dust processes such as evaporation, condensation, crystallization, and isotope exchange in protoplanetary disks, as well as the synthesis and diversification of organic matter from the sun's parent molecular cloud to small bodies through laboratory experiments. He led the development of the Hayabusa2 sampler system and was responsible for the initial analysis of samples returned from the carbonaceous asteroid Ryugu. So please join me in welcoming Dr. Tachibana.
Yep, thank you so much for having me here. Thank you, Yuri, for the kind introduction. It's a great honor for me to share the results of the Japanese asteroid sample return missions, Hayabusa and Hayabusa2. And then today, I'm going to focus on the results from Hayabusa2, in which I was deeply involved. And I'm also going to a little about the future mission. So let me begin with this photo. So we are here as a result of a series of beginnings. Our universe was born 13.8 billion years ago, and the Milky Way galaxy was born around 13 million years ago. And in the galaxy, many stars were born within dense gas cloud called molecular clouds. This is the image of one of the star-forming regions by JWST. And the Sun was one of such stars born 4.67 billion years ago. And around infant stars, protoplanetary disks form as a natural consequence of star formation. And this is the place where planets formed. And within these disks, dust, small tiny particles accrete into small bodies called planetesimals that eventually form planets. And the Earth is one of such planets covering ocean on the surface, and the life was born on the Earth. So let me now focus on the origin and formation, early evolution of the solar system. This is a very schematic view of the solar system formation. The solar system formed from nuclei formed in ancestor stars in the galaxy. And in the sun's parent molecular cloud, volatile elements such as carbon, hydrogen, oxygen, nitrogen start to form molecules, ice, and organic matter. And 4.567 billion years ago, the molecular cloud core collapsed to form the infant sun, and the sun's protoplanetary disks formed around it. And within the disk, various chemical reactions occurred to form chemical diversity within the disk. And the diverse small bodies, planetesimals, formed as the first object in the disk. And such diverse small bodies were ingredients of planets. So this gives the initial state of the planet formation. So these are the key questions we want to know to understand the solar system formation as a result of a series of beginnings. And then the answers of these questions may be found in primitive small bodies formed here, which formed in the very early stage of the solar system evolution. So because they are the object that will keep the information on the initial state of the solar system and gave the initial physical and chemical condition of planet formation. So it's quite important to study such small bodies. And then samples from those small bodies have been known as meteorites we have on the Earth. But it had not been fully understood where meteorites are exactly from. So JAXA, Japanese Space Agency, plan to explore asteroids which are considered to be parent bodies of meteorites, and sent a spacecraft Hayabusa to S-type asteroid Itokawa, and then we successfully completed the first sample return mission from an asteroid. In 2010, the Hayabusa spacecraft returned about 1 milligram of material from the asteroid. And the total amount of the return sample was not huge, just only 1 milligram. But the detailed analysis revealed that Itokawa grains, you see that this is one of the large grains returned from Itokawa, but its size is about 0.1 millimeter, so 100 micron, which is about the diameter of your hair. But this is a beautiful rock. You see a different contrast in this image. That means this is a rock composed of different minerals. And the detailed analysis of these rocks revealed that Itokawa grains are compositionally similar to equilibrated ordinary chondrites, not only compositionally, also mineralogically and petrologically. And it was confirmed for the first time that S-type asteroids are the parent body of ordinary chondrites, which are the most common type of meteorites found on the Earth. And we also found the detailed history of Itokawa from the beginning to the present. And through the analysis of Itokawa grains, it was found that Itokawa underwent thermal metamorphism at temperatures around 800 degrees C, which led Itokawa particles to forget most of the information on the early stage of the solar system formation. So Itokawa particles may not be a good sample to understand the solar system formation. But this Hayabusa mission was an engineering mission to show the ability of JAXA to make a return trip to an asteroid. So in the second mission, so following the success of Hayabusa, JAXA aimed to explore a C-type asteroid Itokawa. This is the science-oriented mission. The reason why JAXA decided to go to C-type asteroids is this. C-type asteroids had been hypothesized to be parent body of carbonaceous chondrites that record the early evolution of the solar system, and some of carbonaceous chondrites contain water in the form of hydrated minerals and organics. So these materials may have been delivered to the early Earth as a source of water and organics. So ocean and life may be formed from these materials. So Ryugu, one of C-type asteroid, seems to be one of the best science targets to be explored to advance our understanding of the solar system, the origin and evolution of the solar system. So through the study of C-type asteroid, we expected to trace back the solar system history to the very beginning, even to the stage before the sun's formation. So Ryugu may provide some answers to these questions. And also, Ryugu's siblings could have delivered water and organics to the early Earth, so which are important ingredients forming the ocean and life on the Earth. So the mission, the Hayabusa2 mission, considered that Ryugu is a very unique target, not only to trace back to the beginning, but also to understand the formation of planets in the solar system and the delivery of volatiles to the early Earth. So now I will show, so Hayabusa2 was launched in 2014 and came back to the Earth with samples in 2020. So 6 years and a half mission. Here I will show 3 minutes video summarizing the 6-year journey of Hayabusa2. So it's very quick. So it was launched in December 2014, and this is the spacecraft. Along this direction, it's about 6 meters. It's a Hayabusa2 in Japanese. After 1 year of launch, the spacecraft made the Earth swing by for acceleration and changing the direction. And it took 3 years and a half to get to the asteroid. And it started the proximity operation. And these are the small hopping robots on the worked on the surface of the asteroid. This is a movable lander developed by CNES and DLR. And this is a practice operation of the landing for sampling. And the first landing for sampling was made in February 2019. I will talk some of the details later. And then this is how the spacecraft collected the sample. And after this operation, spacecraft deployed this one. This is an impactor. After 40 minutes of deployment, it explodes and made an artificial crater on the surface of Ryugu, and we found about 15-meter sized crater on the surface. And the second touchdown was made nearby the artificial crater. We expected to have some subsurface samples as an ejector of cratering operation. And after this second touchdown, so the team made some engineering test operations for future missions. And then in November 2019, the spacecraft left the asteroid. Yeah, we did some, this is another lander, and it left the, so this is the return to the Earth, and I will talk more details later, so I will skip this part. So here is a brief summary of the Hayabusa2 findings at Ryugu, and the Ryugu has a spinning top shape with an equatorial ridge. Its size is about 900 meters in diameter. And so you see many surface borders on the surface. And then, I forgot to say this one. And its bulk density was 1.19 plus minus 0.03 gram per cubic square centimeters, which is smaller than the typical density of carbonaceous chondrites. So this low bulk density and the presence of many surface borders indicates that Ryugu is a rubble pile body formed by accumulation of broken pieces of the ancestor asteroid. And its surface is really dark, like this, and with bluish and reddish tint. I hope you can see something here. And its albedo is about 0.02, so only 2% of light is reflected. And the spacecraft found ubiquitous OH vibration feature at 2.72 micron, which is a strong indication of the presence of hydrated silicates. So minerals contain water in the crystal structure. But this vibration feature was shallower than typical hydrated chondrite. So Ryugu, at that time, we thought Ryugu may have been dehydrated or may have underweight a smaller degree of aqueous alteration, the reaction with water. So, so now let me talk about touchdown operations for sample collection. We did 2 touchdown operations here and here near the equator. And then this is a close-up image of the landing location for sampling. And you may be able to see many dangerous borders. And then this was our target place. And then here I showed the spacecraft as a comparison. So this is about the size of the spacecraft, but we did it. The spacecraft made a landing operation here. And I was in charge of the development of the sampling system. We called it sampler. From scientific point of view, we aimed to collect minimum 100 milligrams, 0.1 gram of samples from multiple surface locations without any terrestrial contamination, which should allow us to analyze the samples with the state-of-the-art technique in 2020. We started the development of the sampler in 2009, so we were talking about the future here. So, and then here, the movie on the right shows how the spacecraft collected the sample on Ryugu. At the time of touchdown, the spacecraft shot a projectile, and then ejector is stored in the sample canister, and then the sample canister is enclosed in the Earth return capsule. Okay, and then the projectile was 5 gram tantalum burette. Okay, here's a movie of the first touchdown operation. Yes, and then at the timing of the touchdown, the projectile was shot. And then this movie was taken by a camera that was made using a public donation. And so this camera was not a scientific instrument, but thanks to this one, I was able to publish a paper in Science Journal. I really thank this camera. And the spacecraft made an artificial impact experiment in April 2019. You showed an animation. I showed the animation previously. And then here, I will show the real movie of the impact. The impact event was captured by a small camera deployed from the spacecraft at the same time of the impactor. You see the ejector formation. And then we confirmed about 15-meter size crater made on the surface. And the second touchdown was made 20 meters north from the artificial crater, and we expected to collect some subsurface samples as an impact ejector. And then this is the movie of the second touchdown. Yes. And then because the asteroid has a really tiny gravity, and you see many flying pebbles. And the pebbles were lifted with the spacecraft. And the very interesting adventure to Ryugu ended with the successful landing of the re-entry capsule in Australia on December 2020. Here you see a beautiful trajectory of the capsule flying over a desert in Australia. Now I show a short video on the day of capsule recovery. And you see this is the capsule flying over the sky. The capsule entered to the atmosphere at the velocity of 12 kilometers per second. And this is the operation room at ISAS JAXA. So now the team is going to detect the signal from the landed capsule. We put 5 antennas on the desert, and then so the direction of the signal detection, the intersection of the direction should be the place for the capsule landing. And we found the place to be headed. So now the time to go to find the capsule. This is me. I was on this helicopter to recover the capsule. It actually took longer time than we expected. And you may be able to see white stuff on the desert. This was a parachute. This happened in December 2020, so it was during the COVID time, so everyone was wearing a mask. And this is a chute, and next to this chute, you see a capsule. So the helicopter landed a bit away from the capsule to avoid any effect from the wind of helicopter. And yeah, this is me wearing my favorite Japanese baseball team jersey, red one. Yep. And we finally found the capsule, and this is the photo I took just after we found it. And this is me with the capsule. And then the team transported the capsule to the base, and the sample container, which was expected to contain the grains, was taken out from the re-entry capsule. And this is the sample container, which is like this big. It's not big. And the container was then connected to a vacuum line. And on the next day of capsule landing, the gases inside the container was extracted, analyzed, and then stored in gas bottles. And after this operation, the sample container, re-entry capsule, gas bottles were safely transported to ISAS JAXA from Australia to Japan. And we had 3 days and a half tireless preparation operation for the container opening. And one of these people was me, but I don't know which one is me. But this operation went very smoothly. It took 3 days and a half, but it's all went well as planned. And we wanted to open the sample container inside the vacuum chamber. So that is why we need to have many different kinds of operation. And we opened the sample container in the clean chamber system dedicated for the Hayabusa2 return Ryugu samples at JAXA. And we opened the sample container about a week after the capsule retrieval operation. And here you see the dark stuff here. And this is about 5 centimeters. So you have an idea of how large these particles is, a millimeter size to a few millimeter size particles. And these are the samples collected during the first touchdown operation. And the second touchdown operation sample was stored in this part. So we separately stored the sample inside a very small size of sample canister. And this is the first touchdown sample, and these are the second touchdown sample. And the total amount of the sample exceeded 5 grams, which was 50 times more than the mission requirement. So we are really happy to see these many particles. This 5 gram was actually the largest amount returned from deep space beyond the Earth and Moon system. But this world record was broken by OSIRIS-REx Bennu samples, 121 grams. And to unravel the history of Ryugu in the context of the solar system evolution, the Hayabusa2 project team established the initial analysis team comprising 6 sub-teams: chemistry, mineralogy, and petrology of coarse grains, and those for fine grains, volatiles, and the macromolecular organics led by Hikaru, sitting over there, and the soluble organic molecules. So the team analyzed the Ryugu samples using different disciplines, and and the total number of researchers involved in this activity was about 400. So we really thank all of the members who contributed to this analysis. And the team got about 300 milligram of the samples, which is 6% of the total mass, from both touchdown sites. And then these are the 22 particles we analyzed, and here's a 1 millimeter scale bar. You see the size of the particles, mostly 1 millimeter in size, except for this one. This is the third largest grain we returned. It's about 9 millimeter in along this direction. And we also analyzed 10 aggregate powdery samples as well. So now let's move on to the results. And this is the centimeter size grains. And the grain was first investigated using synchrotron XSCT. And then you now see the inside of the sample. And you may be able to see a difference in contrast, which suggests the presence of different types of lithologies inside the grains. And then these white sparkles are iron sulfide and iron oxide. And you may also notice that this grain contain no chondrules or CAIs that are high temperature objects formed in the early solar system. Oh, I now have a replica of this grain. This grain was gone. We crushed, dissolved, and we cut. So this is our memory. And this was made by the 3D printer. Yeah, please take a look. And through the analysis, the team has published about 100 papers that are related to sample collection and analysis. And I don't think I have time to explain all of those papers. So I will focus on some important findings in this talk. But a huge amount of papers are coming out from 5 grams of samples. 300 milligrams of samples. So first, let me compare the visible and the infrared reflection spectra of the grains with real Ryugu. And the left panel shows the return samples were as dark as the surface of Ryugu. And so these are the Ryugu samples, and these are the spacecraft of observation. So reflectance is 0.02, so only 2% of light is reflected. And then this one shows the infrared, near-infrared spectrum of Ryugu grains. This is from touchdown 1 side, and these are from touchdown 2 side. And this light green is the spacecraft observation of Ryugu. And you see this 2.7 micron absorption feature is much weaker for the spacecraft observation compared to the real sample. This means real samples contain more water compared to the Ryugu observation. And then this was supported by the observation of the grains. And the Ryugu samples, Ryugu grains contain phyllosilicates, saponite and serpentine. 80 to 90 volume% of the grains consist of phyllosilicates, along with carbonates, iron sulfide, and magnetite, which is iron oxide. And this mineral assemblage suggests that the samples are highly aqueously altered. So liquid water was once there on Ryugu. And it's also noteworthy that Ryugu's mineral assemblage, this mineral assemblage is the same as that of Ci chondrites, one of the carbonaceous chondrites. And they are highly altered meteorites. And based on the oxygen isotope analysis of dolomite, which is one of the carbonates, and the magnetite showed that the precipitation of these minerals occurred at 37 plus minus 10 degrees C, which is about 100 Fahrenheit. 4 million years after the solar system formation, this date was determined by manganese-chromium dating. And the team truly discovered ancient liquid water. Actually, Mike did this finding, and from that grain, so someone has the 1 centimeter grain, and through the X-ray CT analysis, the team found a void in this beautiful hexagonal-shaped iron sulfide. And Mike put this grain onto a cold time of flight mass spec, and at the temperature of minus 120 degrees C, so he analyzed this void, and they found water with organic matter and also CO2. So the water found in this iron sulfide is a real ancient water present in Ryugu. And the likely source of CO2 found in this fluid inclusion could be CO2 ice in the outer solar system, in the cold part of our outer solar system. So this implies that Ryugu may have formed in the cold outer part of the solar system. So there are many interesting findings, but one of the interesting findings was the record of paramagnetic field found in flamboidal, in a 1 micron size tiny grain of iron oxide. And this is taken by a transmission electron microscope, and you see the magnetic field recorded in each grains. And the intensity recorded in these magnetite grains was around several hundred microtesla, which is strong, which is not the magnetic field is predicted for the outer solar system. And this intensity of magnetic field seems to be that in the inner protoplanetary disk. This indicates that at the timing of the formation of this magnetite, which happened 4 million years after the solar system formation, Ryugu may have already been transported to the inner solar system. So Ryugu may have formed in outer solar system, but may have already been transported by the time of the precipitation of this magnetite. So here I present, let me talk about chemistry. Here I present the elemental abundance of Ryugu samples normalized to Ci chondrites, which is the most similar type of meteorites to Ryugu samples. We analyzed 66 elements using different techniques. And the data show that Ryugu's chemistry closely matches that of CI chondrites. And we know that CI chondrites have the elemental composition very similar to that of the Sun. So CI chondrites have been used as an representative, used as a sample having a representative solar system elemental abundance. So the Ryugu's chemistry matches the CI chondrites, which means Ryugu's chemistry is very similar to that of the Sun. And isotopically, Ryugu seems to be close to CI chondrites. Oxygen, chromium, titanium, iron, zinc, calcium, copper, nickel, those isotope compositions are also similar to CIs. And here I show a plot of titanium and iron isotope systems. And then, so this is the group of carbonaceous chondrites. And this is non-carbonaceous chondrite group. And the Ryugu and CI comes here. And this is a diagram showing different nickel isotope compositions. And this is non-carbonaceous chondrite group, this is carbonaceous chondrite group, and Ryugu and CIs come here. So we have been discussing about the presence of dichotomy, isotope dichotomy in the solar system, but concerning CI and Ryugu, there may be trichotomy, or we don't have any dichotomy. There may be a continuous distribution of isotopes in the solar system. And so actually people have known CI comes here, but we have only 10 CI chondrites in the meteorite collection. We have about 70,000 meteorites on the Earth, only 10 CIs. So CIs seems to be a very minor component of the solar system. So we haven't discussed about NC and CC groups, but CI and Ryugu is a C-type asteroid, which is the main asteroid in the asteroid belt. So we cannot ignore CI-type materials anymore because Ryugu sample is CI-like and from a major type of asteroid. So yeah, we look forward to more data for the analysis of isotopes from Ryugu samples and then CIs. So now I will talk about light elements. The carbon abundance of Ryugu samples is about 5-8%, which is among the highest. I'm sorry, I don't have the abundance data. And the left two panels shows the hydrogen, nitrogen, and carbon isotope compositions of Ryugu. And the Ryugu sample is not exactly the same as those of the Sun, but close enough compared to the comet. This is DH ratio, heavy hydrogen and light hydrogen ratio. This is as the ocean, this is Ryugu, and these are the comets. So Ryugu's hydrogen isotope abundant isotope composition is more or less similar to Earth compared to comets. And Ryugu contains about 5% of carbon, as I mentioned, and 2/3 of which is present as organic matter. And here I show the plots from Hikaru's paper. And some of the organic matter is present at submicron-sized organic globules, like this. And some of those globules shows the isotope anomaly containing heavy hydrogen, deuterium, and nitrogen-15. And some of them have depletion of deuterium. So such an isotope anomaly can be related to the low temperature chemistry in the Sun's parent molecular cloud, the chemical reactions before the formation of the solar system. The plot on the right shows the data from Sarah Zeikner, the John Eilers group, and then John and Sarah found that some of the Ryugu's PAHs, polycyclic aromatic hydrocarbons such as naphthalene and pyridine and fluorantine, shows the peculiar carbon-13 composition, which also may relate to the low temperature chemistry. So Ryugu underwent heavy aqueous alteration, but some of the organics may still be, may have survived such a reaction and then still exist in the Ryugu sample. And we also see the many evidence of organic evolution during aqueous activity. Here in the image from Hikaru's paper, we see a very close association of diffuse carbon, which is shown in the purple color, with phyllosilicates, which is shown in green. And then here you see a good blend of pinkish and green color. And then the image on the right also shows the close association between minerals and the organic matter. So diversification of organic matter also occurred on Ryugu. And then such molecular evolution during aqueous activity resulted in finding of more than 20,000 molecules in Ryugu samples. And in these tons of molecules, the team found prebiotic molecules such as amino acids and nuclear bases, and more than 20 amino acids. You may not be able to see this, and then here's a list of amino acids found in Ryugu, and including both protein and non-protein amino acids, and all present as a racemic mixture, indicating that abiotic synthesis of those amino acids. And the Ryugu also contained uracil, which is one of the nucleobases that make up RNA in the terrestrial life. And after finding of uracil, so I recently heard that list of 4 nucleobases have also found being also found in Ryugu samples. So Ryugu contains 5 nucleobases that makes up RNA and DNA. And again, I'd like to emphasize that these molecules were synthesized through abiotic processes. So this suggests that prebiotic molecules were prepared in space before being delivered to the Earth. And the Ryugu samples were found to be enriched in volatile elements such as noble gases. And as shown here, the abundance of argon and krypton and xenon are among the highest compared to meteorites. And let me skip this one. And one more topic about noble gases. So as I said, we extracted gases inside the sample container. And we sent those gas samples in 5 different noble gas laboratories in the world. And the results came up here. This is the helium isotope and the neon isotope diagram. And this is Earth's atmosphere, this is solar wind. And the data shows the mixing between the air and the solar wind. And we unfortunately had a tiny air leak, but this container gas shows that we could return solar wind noble gas. So I think this is the first returned gaseous samples from space. And the team discovered that several percent of Ryugu grains have space-weathered surfaces, as shown here. And then these space-weathered surfaces are dehydrated and amorphized, and which may explain the shallower OH absorption feature of the spacecraft observation. So space weathering may hide the true hydrous nature of Ryugu. So we learned a lot from Ryugu samples from the very beginning to the very recent stage of asteroid formation. And what is important next is to compare the samples, the result with Bennu. We now know that Bennu sample is also similar to CIs and Ryugu. And so 2 spacecrafts went to 2 different asteroids and brought back CI-like materials. So there may be a lot of CI-like materials in the solar system, but however, they are very fragile, so they cannot survive the atmospheric entry. So I will skip this one. And then, so because of the potential importance of Ryugu samples as a new elemental reference of the solar system, so Ryugu may have the solar system elemental abundance. So JAXA has started the Ryugu reference project in which the average abundance of nuclei elements in Ryugu samples will be determined through the analysis of homogenized Ryugu powder. And in the slide I showed before, we just used 25 milligram of Ryugu powder, which is not homogenized. So we may see some heterogeneity in the sample. So we are going to make a Ryugu homogenized powder. And what is JAXA's next destination? That is Phobos. JAXA plans to send the MMX spacecraft to Phobos, one of Martian moons, and by analyzing samples from Phobos, the mission team aims to uncover the origin of the moons in early 2030s. So Phobos may be a captured asteroid or may be formed by giant impact. So now the JAXA creation facility has 3 asteroid samples, Itokawa, Ryugu, and Bennu, which was delivered from NASA last summer. And so JAXA itself has had small body sample return missions every decade. Itokawa, Ryugu, and MMX. And I hope this will be continuing to make contribution to the solar system science. And the samples are now available to the community, and so far 75 milligram of the Ryugu samples has been allocated to the community. And the call for Ryugu A06 and the Bennu A01 has just opened, and I realized that the notice of interest submission due is tomorrow. So if you are interested in, please do that tonight. And I want to add one note here. Not only the detailed analysis of return samples, but the linkage with different disciplines will further broaden the science of return samples, such as laboratory experiments, which I do love, and astronomical observations, and simulations, and modeling. And so that kind of linkage will be quite important after getting the samples on the Earth. So this is, I'm getting close to the end, the final slide showing my lessons learned from the sample return missions. And yeah, these 3, and then this, this is my biggest lessons learned. Thank you for your kind attention.